in our next question, we're going to talk about the stars all over again. In Python 3.0, we gained keyword-only arguments via PEP 3102. And you've seen this before. You have variadic arguments and variadic keyword arguments in pure Python. You have the star args and the star quargs. This means this function could take any number of additional positional arguments and any number of additional keyword arguments. And PEP 3102 adds a function that looks like this, a function which can take this argument x only when passed by keyword. Let's talk about the first part here. The first part here, just to show you, here we have our function. And depending on how I call this function, we'll see that that args parameter and that quargs parameter get filled in. If I pass a bunch of positional arguments, they get filled into args as a tuple. If I pass a bunch of keyword arguments, they get filled into quargs as a dictionary. The names of these, this is the canonical names, but you can call them anything you want. You can call it A and KW, call it anything you want. And this function is quite universal in the sense that it can take no arguments, it can take 10 positional arguments, it can take 15 keyword arguments, it can take any mix or match. And the only requirements that you have is, as usual, you can't specify keyword arguments before you specify positional arguments. That could be ambiguous. But otherwise, you can pass anything to this. For the PEP 3132 keyword-only arguments, what's that all about? Well, here this function can only take this argument x if passed by keyword. It cannot take this x if it's passed, and let's fix our typo here, if that is passed positionally. And you might wonder, why does this all matter? Well, let's say that you're the author of a tool like Pandas, and in Pandas, you write a function like readCSV. And by the way, that's the signature for readCSV. It has 50 total parameters. Or let's say you're the author of a library like matplotlib, and you author something like matplotlib.hist. And let's take a look at how many parameters hist for creating a histogram has. It has 17 total parameters. You say, I am deadly afraid that I'm going to be reading some code where somebody said readCSV, filename.csv, comma, none, 0, 1, true. And I'm going to have no ability to make heads or tails of what the heck this does. I have no clue what those parameters mean. This is kind of like, if you've ever read C code, since C code doesn't have keyword arguments, sometimes you see like an argument and then like a null, 3, null, and you're counting the nulls and you're like, wait, is this 3 here parameter F or is it parameter X? And you're just trying to match these up and it's a real pain in the butt. Well, what you could do if you're the author of a library like this is you could force these to be keyword-only arguments. You could say, oh, this is index call, this is headers, and I guess for true, I'll say squeeze. That's one. And now you can actually make heads or tails of it, and you can see maybe there's a little bit of judgment here. Do you really need to say delimiter equals comma, or is it obvious that if it's a CSV file, the first argument's going to be the file name and the second argument's going to be whether it's a tab-separated file or a pipe-separated file or whatnot. And similarly, you could maybe say, oh, let's pass all arguments by keyword, but I think that's a little bit overkill because if it's a function called readCSV, probably the first argument's the CSV file you're going to read, so maybe you don't need to force that. Similarly, for hist, you could do the same thing. Now, here's something I want to share with you. If you look at functions that you define, it is often the case that those functions tend to bifurcate their arguments into 2 broad classes. Class 1 is the arguments, the parameters that correspond to data. And class 2 are the arguments that correspond to metadata. Data, broadly being the input that the function operates on. Metadata being something that affects the way in which we do the operation. It is often the case that metadata is optional and has some sort of default. So this is some function that operates on some data, and the data is required. The function, you can't do anything if you don't pass in the data. But there's a flag like read only, or there's a flag like dry run, or there's a flag like timeout. And these are all modalities. These are all pieces of metadata or some sort of modality that indicates how We are going to go about doing the process, not what we're doing it on. Now, it's very common that these might be keyword-only arguments, because if you think about it, the modalities oftentimes are the place where people have the most questions. For read CSV, obviously, one of the arguments is going to be the CSV file that you are going to read in. It's in the name. So that probably doesn't need to be a keyword argument. For hist, one of the arguments is going to be the data that you're going to generate the histogram off. That doesn't need to be a keyword argument. We know that one of the arguments there has got to be the data. But the flags for it, whether to do a cumulative distribution, whether to do a weighted, or what the weights might be, whether this should be a density-based one, so it's normalized, those are all modes that we want to make very clear. And so where PEP 3132 keyword-only arguments allow you as a library author to make your code more understandable is by identifying the parts of some function, the parameters that represent the modalities, and forcing somebody to identify what mode they're operating under. The data itself, we know that this function takes data, but the mode is critical. Now, there's another layer to this. Let's say that you work in an organization where there is some team that has some core APIs, and you're responsible for bringing those to the end users. So you have some central technology group, and you don't belong to the central technology group because you like to be close to the action. You work with the line of business, and you take the stuff that the central technology group creates and you adapt it for the use of the line of business, which means adding inconveniences that do things like hard code modes, which are relevant to your division. For example, you might say, you know what, for our purposes, this mode flag is always true, but maybe this flag parameter might be true, might be false, we're not quite sure, so we'll let somebody pass that in. So we'll hard code one of these because we don't need people to be typing mode equals true all the time, and maybe we have some new hires in the line of business and they may not know whether they want that mode turned on or off, but we can say, for every one of our use cases, that's an assumption that's made within the entire line of business, even though the core technology group, who has to support multiple businesses, can't make that as a global operation. Now, here you can actually see 3 layers of code. There is the library author for the core library, there's the library author for the convenience, and then there's the library user. Here, this is like some core technology group at a bank, this is like the technology group that works with the line of business, and this is like the traders. What will happen is, at some point in time, the core technology group are going to add another mode. And when they add another mode, the person who is most likely to be aware of that, I find, is actually not the technology people who are sitting in the middle, but the actual end users. It's not unusual in my experience for the end users in many ways to be closer to the action, especially if this is open source code that you're wrapping, especially if you're the internal developer at the company and this is some third-party tool. It is not unusual. Because if you think about it, your users are in and out of this function every single day. And they're in and out of all the supplementary libraries that use this function every single day. And they're so intimately related to the underlying problem that they know, oh, this now has an additional way of doing it. The industry is moving in this direction. We saw some new papers and machine learning algorithm has changed slightly, and now we have an additional parameter for our machine learning algorithm. They tend to know that. And it's not unusual that when you're writing convenience libraries and you're sitting in the middle, you're going from one project to another project to another project, and you're not maintaining this one convenience layer all the time. And so when this modality gets added here, these people down here find out about it before you do. And they come to you and they say, can you help me add this mode? I know this came out. I've been reading the pandas change logs. And you're like, I don't even have time to read the pandas change logs. You're a trader. How do you have time to do that? But surprisingly enough, they are so intimately involved in the problems that they solve and so motivated to use these tools effectively that they may find out this beforehand. You really don't want them to come back to you and say, you know that thing you did for me last month, that convenience layer? Can you extend that convenience layer, please? And to constantly be chasing down those extensions, especially if it's not on your schedule, especially if it's them having to drive this, because you may have put this convenience project off to the side to work on something that for you and your team, your technology team, is more important or more critical. What you could do here is you could use keyword arguments. And what you can think is the value of keyword arguments is not just, oh, let me write a function like print that can take any number of arguments. It's also let me write layers that are transparent to other layers of my code. With keyword arguments here, this addition up here is transparently passed through when that changes. And if you think about it, what if this layer here changes the default for the flag? Well, actually here, you know what? I'll pass all of these through. And so I don't need to even worry about that. So now you can be responsive to those flags. And you can do some really neat things. Like you can say, oh, if somebody wants to override this mode, you could even do this. Take the keyword arguments you're passed, unpack them into a dictionary, and then you could say mode equals, actually we'll do it this other way. We could do this. And this here you can think is even better than what we had before, because this says take any number of additional keyword arguments. If mode wasn't set, force it to be true, unpack the rest of the keyword arguments after it. And so let me actually write this correctly. Unpack the other keyword arguments. So if somebody wants to say mode equals false, they can override that. But otherwise, you fix this mode even if the core authors change their defaults. So you have the ability to write these really nice transparent layers. And this matters because you want that level of transparency, especially because your end users will otherwise be chasing after you. Can you add this? Can you add this? Can you add this? You really want to write, when you write a convenience layer, make the scope narrow, get it out, and try and make it as transparent as possible to changes that happen at the core layer or demands that may come to you from the convenience layer. Because otherwise, you're just constantly coming back to this project and you're never going to be able to do other work. I want to show you one other thing about star arguments that people don't usually talk about, and it's a mistake in the standard library. It's a mistake, actually, it's a mistake in the built-in functions. There is a function in the Python built-ins called isInstance, and it allows you to determine whether an object is an instance of something. Is this an int? Is this an int or a float? And there is a mode where you can pass multiple, here 2 types in a tuple. And so you might say, oh, if I'm checking if this thing is constantly an instance of my special class and my special class, I'll use a tuple. And I don't want to have to write int float or my class 1, 2, and 3 over and over. So I'll put this into a variable types that looks like this. And then everywhere I can just write, oh, is this thing one of my trade types or whatever type of problem you have. And then sometime later, you're going to look at this and say, you know what? I don't care the order. Int float's the same thing as float int, so I'll put this into a set. And this will fail because the isInstance function needs as its parameter a tuple and only a strict tuple, and anything else will not work. And so now you'll say, oh, you know what? I really like this being a set because it indicates that there's no specific ordering relationship. And I think the use of a tuple here is kind of a little bit hokey. And so now what I'm going to have to do is use something like my unpacking syntax every time I call this to forcibly unpack this into a tuple, and that's just really ugly. Well, here's the thing. If you were to look at how that isInstance function works, it takes 2 arguments. The first argument being the value, the object that it's trying to figure out, and the second one being either one type or a bunch of types in a tuple. And there has to be some logic in this isInstance function that disambiguates. Do they pass me one thing or do they pass me multiple things? And maybe it looks something like this. If they passed you multiple things, or if they didn't pass you multiple things, then you pack it up here. And actually, I should do it like this, because this is not correct. Oh, or you can put a for loop here, or I could do something like, just to reuse this thing, I could do something like this. And so there we go. That's maybe how it works. However, here's the thing. Anytime you have an argument to a function, and it could be either one thing or the other, it could be one individual element or multiple elements, you have to make sure that you can disambiguate the 2. And this can be very tricky to do in practice because, remember, you're not guaranteed to be able to disambiguate something that is a type that you want to check against. Anything that is instance check could be a type that you want to check against. Additionally, anything that implements iter could be iterable. And so here you can see this meta class, when applied to any class, makes that class checkable and customizes what that checking does, and makes that class iterable and customizing what that iterability does. There is a default instance check, of course, it actually checks the concrete types, but here you can see that any custom class could get both of those behaviors and disambiguating between, wait, is this the type that I want to check against, or is this an iterable containing the types I want to check against? In generality, is not possible. As a consequence, they can't change isInstance to allow any arbitrary iterable, and My argument is this suggests that the API is wrong. If they had written the API using star args, this would be unambiguous. Because star arg says I take 0 or more arguments. They could add a check here to make sure that, if len types equals 0, you fail. Or they could have said, type 0 and then types 1 to whatever, something like that, to force the signature to allow that. These are all sorts of different tricks people use. But irrespective of which of those two techniques they use, this argument here is always unambiguously a container. It never has that question of, are you a container or are you an individual element of data? And remember, from the last seminar, we said there are many contexts in which there is an ambiguity. Remember, NumPy considers strings to be elements. It considers them to be datum, whereas Python considers strings to be containers. It considers them to be data. And so it can be very ambiguous. Wait, is this the one thing that I want to work on or the collection of things I want to work on? The star unpacking syntax like this allows you to actually disambiguate those, allow you to make these unambiguous. And in the type situation, then you'd have some syntax. It wouldn't be that ugly, but it'd be a little bit consistent. It would be, not too bad. You would just say, star unpack my types. And I think even though there's an unpacking, even though there's a copying of some structure, I do think that this is maybe a little bit more tolerable than taking something that's in a set and unpacking it into another type of iterable just because the function requires it one way. Now, there's a somewhat related problem. Many of you have seen decorators, and we won't talk about decorators or advanced topics too much because we're talking about Python basics. But if you've seen decorators, you know that you can have a decorator that applies to a function. And you may have even seen decorators that take arguments that then create the decorator that apply to this function. And you may have even seen attempts, and there's libraries out there that try and do this, of people who say, you know what, if this thing doesn't take any arguments, I really hate to put the open-close parentheses, so I want to be able to support either this syntax, where the thing that's being sent into this decorator is the function, or this syntax, where the thing that's being sent in are the arguments that parameterize the decorator, and then the result of that gets sent this function. And you can see it's another one of the same cases where this argument here could either be the function or the arguments. And you don't know which they are, and you have to disambiguate. And you can think that if the parameters for your decorator could include callables themselves, it may be impossible for you to disambiguate. And so all of the libraries that do this, allow either of these syntax, they're actually quite dodgy because what they use, all the ones I've seen, they'll use the inspect module to look up the source text and to figure out from the source text which of these two syntaxes you used. And that is very dodgy because there's no guarantee that the source text for a function actually exists. And there's no reason why it shouldn't be valid to use a decorator like this or to use a decorator like this. There may even be cases where you want to do that, and you need some slightly more advanced syntax in order to be able to check that. And if for whatever reason the source code for this doesn't exist, for example, this becomes Pythonized, well, the whole thing falls apart. I think the answer to this is anytime there's an ambiguity, you want to find a way to eliminate that ambiguity. One way you could do that is say, you know what? This thing is either strictly a function or some keyword arguments, and this could be set to none, and the parameters to my decorator must always be keyword arguments. I think that's reasonable. That disambiguates it. Or you could say, this decorator doesn't meaningfully take a function as its first argument. That meaningfully disambiguates it. There are a bunch of options, but fundamentally you can see it's part of the same underlying pattern. And that may lead you to why this slash here exists. This slash separates positional-only arguments from the rest. A can only ever be passed positionally. What you could think is, in the decorator circumstance, maybe that's what you want. Maybe you want to say that F here has a default, and it can only be passed positionally, and so now it is unambiguously distinguishable from these keyword arguments, and that means that this decorator syntax must always take keywords. And you might say, well, you know what? A decorator is a kind of modality. It usually introduces modalities into something, and so it's fair for a decorator to either have this syntax or this syntax, but it can't have the positional argument passing syntax in the middle, and thus I can actually, disambiguate this and write a function.